Okay, so the plan for today is to work through, see how far we get in 11.3, the integral test, and 11.4, the comparison tests. Um, and then I'll probably kick to a supplement anything we don't get through today, as well as those last couple of applications from series from last week. So I'll probably just put those all in one supplement this week. The quote of the day today is by philosopher David Hume. A wise man always apportions his belief to the evidence. So this probably goes more for scientific type beliefs, right? That we look for evidence in support of rather than um, other types of argumentative support. But so I think it's also important to take this in the context of the so-called Hume's guillotine, the is-ought problem that uh, science and evidentiary support are very good at making is statements, but ought statements, how should we proceed, is often a combination of those is statements with things like social norms and morals and values and all of these kind of things, trade-offs and all of that, kind of all wrapped up together. So, um, but yeah, so that's the quote for today. Okay, so moving on to 11.3, the integral test. And just a kind of a really quick, 30,000 foot overview, we saw in section 11.2, kind of at the very beginning, we had the definition of convergence of a series. So a series being an infinite sum, say, such as this one. And we saw that some series diverge, some series kind of like shoot off to infinity, some series just kind of wiggle around a little too much and never really settle down. And some series converge. Some series have terms that get small enough, fast enough that we can add infinitely many of them together and get a kind of uh, reasonable finite sum. We also mentioned that we had very specific definitions. Anytime we're dealing with infinity is kind of being thrown around like this, we have to be very careful about our definitions. And we had certain definitions. And I want to caution you again that if you look up some of this stuff on YouTube or on Google or something, you might find, uh, really cool and interesting videos from folks who are very well qualified, saying things that are slightly different or maybe very different than what we're saying in class here. If you find that, be very cognizant of what assumptions they're making. A lot of times they're working with slightly different definitions than we're working with. And a lot of times they're not being super careful to lay out exactly what their definitions or assumptions are. So I just want to caution you against that, stick to things that are kind of intended to be um, geared towards students in a Calc 1 through Calc 3 series, and you will be much more likely to stick close to the types of assumptions we're making. If you venture out into, physics videos or things like that, or videos, from things like Numberphile or something, they're really interesting videos, but I don't want you to watch those videos and then get thrown off for the course material, right? If you want to watch those videos over the summer because you think it's interesting, go for it. It is interesting stuff, but don't confuse yourself with the existence of some different definitions. I think I gave a little bit of insight into that last time. We also mentioned that this kind of basic definition, convergence of a series, means convergence of the sequence of partial sums and so on. A lot of times that definition is really hard to apply directly. It's maybe a little bit like you think of the definition of a derivative. We, went through a couple maybe proofs in Calc 1, what's the derivative of x using the definition of the derivative, or maybe even something a little more complicated than that. But certainly if I want to compute the derivative of, e to the power sine of x multiplied by natural log of x or something, I'm not using the definition of the derivative for that. I'm using derivative properties to do that. And it's kind of similar here that there are some types of series, maybe like geometric series or maybe telescoping series, where in essence, direct application of the definition is great. It works out just fine. But most series, it doesn't work out so great. It becomes an intractable problem. So what we have is we have some tests. We have ways to make arguments that a certain series does or does not converge. We saw our first of these tests in 11.2 the test for divergence, or often it's just called the divergence criterion, that if the individual terms of the sum do not limit to zero, then the series must not converge and must diverge. We're going to see over the next few sections, we're going to build up some additional tests. These are a little bit like properties that apply to series. And often what they tell us is, here's a series. If I apply this property or this test, the integral test, for instance, the integral test might tell me this series converges, or it might tell me this series diverges. These tests, these kind of properties in a sense, these tests aren't typically going to tell us if it converges what the sum is. So really these tests, the goal of them, of most of these tests, is just to say, does the series converge or does the series diverge? Or perhaps maybe we apply this test and it's inconclusive. This test doesn't really tell us one way or the other. Maybe we have to use a different test. So in a sense, we're developing a new set of tools in a new toolbox. We have this new empty toolbox with, well, I suppose it's not empty. We have, the definition of convergence and we have the test for divergence. We have two tools in it. We're trying to fill up the toolbox with more tools so that we can handle more different types of series. But most of these tools, they only give us basically a thumbs up or thumbs down. It converges, it diverges, and doesn't tell us a whole lot more than that. So I want to just, lay that out. It's a little different than what we're often used to in a math course. We're often used to the conclusion of a problem being this thing equals number, and what does that number turn out to be? This is a little bit more like, it has a feeling a little bit more like, say, the proof of a derivative property, like proving the product rule or proving the quotient rule, and that our end goal isn't thing equals number, but our end goal is, claim this series converges, proof, here's my argument for why it converges. Or claim the series diverges, proof, here's my argument for why it diverges. So has a little bit of a different feel than that. Now, like I mentioned, sometimes we, in some sense, get lucky or fortunate, or, sometimes we can rewrite the series as a telescoping series and actually compute the sum if it converges. Or maybe as a geometric series, we can see that this is going to be the sum if it converges. But most often that's not the case. Most often we're just arguing it does converge, it does diverge, and that's often the end of the story. That's often the end of the problem. Okay, so our first example in the integral test, show that sum n equals 1 to infinity 1 over n plus 1, or n squared plus 1, is convergent. And for this, we're going to use the integral test. These tests are all essentially theorems. It says if a bunch of things are true, then a conclusion is true. As theorems, we need to check that all of the assumptions are true before we apply the conclusion. So it's very tempting to just kind of, put this in our toolbox, but we do need to make sure that we're in a scenario where our assumptions do apply. So if we have a function f that is a continuous, positive, decreasing function on the interval 1 to infinity, and if our elements of our series, if our ANs, if A1 plus A2 plus A3, if each of those individual terms are essentially plucked from this function, if AN equals f of n, then we can say the following, that the series is convergent if and only if essentially the corresponding integral is convergent. And I'm just going to quickly note here, recall, we made kind of an argument. We didn't use the integral test per se, and we didn't really use it in this strong of a form, but we made kind of an argument looking at the harmonic series. We made an argument kind of comparing a partial sum with an integral. And then we showed that this integral went to infinity, which implies the sequence of partial sums goes to infinity. So, refer back to that argument for the divergence of the harmonic series, and it has a feel of what we're saying here, that we can associate sums through this kind of, area of blocks representation, in a sense, with integrals. And the convergence properties of the sums and the integrals, should be kind of similar. Like I said, the integral test is making a much stronger statement than what we made before. We're not only saying, okay, if we can make the partial sums line up this way with something like the partial integrals, then we can make an argument about the limits. We're saying something much stronger than that. But this certainly has the feel of something like the harmonic series argument that we made. Okay, so let's take a look at this example. Let me zoom this in a bit so it's a little bigger on your screen. Show that the series sum n equals 1 to infinity of 1 over n squared plus 1 is convergent. Okay. Since we kind of only have one tool in our toolbox, I suppose we could look at this and ask the test for divergence. Do the individual terms go to 0? Sure. 1 over n squared plus 1 does go to 0, so this could converge, it could diverge. We don't know yet. Our next tool in our toolbox is the integral test. Let's try to apply that here. So if I look at an, it's 1 over n squared plus 1, clearly associated with f of x equals 1 over x squared plus 1. I do notice that on flows 1 to infinity, f is a continuous function. Yeah, there's nothing wrong with this. It actually looks a little bit maybe like a bell-shaped curve kind of thing, almost like a normal distribution. It's positive. Yeah, sure, the numerator is positive, the denominator is obviously positive. And it's decreasing on 1 to infinity. We can check that. So I'll leave it as an exercise to show that f prime of x is negative on 1 to infinity. So f is continuous, positive, and decreasing on 1 to infinity. And of course, an is f of n. So we can apply the conclusion. The conclusion is kind of like another essentially if-then statement. So you could even kind of imagine it like bracketing this off. If the first thing is true, then this statement is true, that the series is convergent if and only if this integral is convergent. So now let me investigate the integral. Maybe I'll switch colors. There we go. So let me investigate the integral 1 to infinity of 1 over x squared plus 1 dx. I'm going to be a little bit more careful than usual here. I'm not going to be too hand-wavy because there's already a lot going on with the series and the integral test and all that. So what would this be? This will be the limit b goes to infinity integral 1 to b of 1 over x squared plus 1 dx. I just want to be very clear about exactly what we are doing. Normally with these improper integrals, I'm a little more hand-wavy. I kind of, do this limiting process more implicitly, and but I'm going to be really careful about writing out all of the details here. Well, 1 over 1 plus x squared, that's the derivative of arctan. Or this is arctan b, got my limit. This is limit b goes to infinity. Arctan b minus arctan 1. And I know that arctan 1, certainly a real number. Limit b goes to infinity arctan b, well, that is just pi over 2, right? So this is a real number. In other words, this integral converges. So my assumptions are satisfied. The associated integral converges. Therefore, the series is convergent. So I can now say something like, by the integral test, sum 1 over n squared plus 1 converges. So there's actually a lot I need to show, but really the crux of the thing is what kind of makes sense from a gut feeling standpoint is that the series kind of behaves more or less like the associated integral. If the associated integral converges, the series converges, and vice versa. If the associated integral does not converge, the series does not converge. It's not super clear that that's the case because, my integral could be overestimating or underestimating the partial sums. So it's not super clear from the beginning that that ought to be true, but it does kind of intuitively make sense that sums and integrals are both essentially representing areas, and if they're representing areas of essentially similar objects, then their convergence properties, it would make sense, would be the same, and that's what the integral test says. Okay, so let's examine this series, sum 2 to infinity, 1 over n log n. So clearly the associated function is f of x equals 1 over x log x. I note that f on 1 to infinity, or 2 to infinity here, we're starting at n equals 2, so we're going to consider the interval 2 to infinity, so we don't have any like log of 1s or zeros floating around in the bottom. So on 2 to infinity, f is continuous. It is positive. Well, it's positive if we're far enough out, right? It's positive for, so log of 2 would be negative, but log of 3, well, now we're positive. And this brings out an important point that series convergence or convergence of a series is really a matter of what happens in the tail, right? I can always consider this sum to be something like 1 over 2 log 2 plus sum n equals 3 to infinity, 1 over n log n. And then the convergence really is just a question of what happens here. Convergence of a series is really a matter of what the tail looks like. So if I have, 1 or 2 terms or 1 or 2 elements at the beginning of the series that don't satisfy some property, but all of my terms satisfy that property after a certain point in the series, well, then I'm safe to use these convergence tests. If I wanted to be super formal about it, I could do this kind of a thing. But I do see that, if I'm being a little bit less formal, I can make arguments like this. I can say, okay, if n's bigger than or equal to 3, we're positive, we can apply the integral test and maybe not write a whole lot more than that. This isn't really a proofs course. The level of formality, that's essentially being asked for in a question like this, I don't want you to write, 1 page of writing dealing with all the little tiny nuances, and then 1 page of writing dealing with the stuff that we're actually trying to learn here, which is ideas about series. So, but continuous positive if we're far enough out in the tail, and decreasing as well. I'll leave this as an exercise, but far enough out in the tail, we're fine here as well. So our assumptions are satisfied. That means the convergence of the series is going to look like the convergence of the integral. What does the convergence of the integral look like? here I've adjusted all of my lower bounds in light of the fact that our series starts at n equals 2 instead of n equals 1. And what is this going to be? This is going to be log of x. If I differentiate log of x, the outside log, I differentiate that, I get 1 over log of x times the derivative of the inside. The derivative of log of x is 1 over x. So the antiderivative of 1 over x log x is log x. We could use a u substitution like u equals log x, du equals 1 over x dx, if you wanted to see it a little more clearly. But we're going to evaluate this from 2 to infinity. And here I'm kind of concatenating some of this business with writing the limit a bunch of times. And what do I see here? As x goes to infinity, log x goes to infinity. And log of log x goes to infinity. This series, or sorry, this integral diverges. And therefore, the series diverges as demonstrated by the integral test. The integral test does apply here because these three assumptions are satisfied. So we can apply the integral test to determine whether the series converges or diverges by looking at the integral. We look at the integral and we note that the integral diverges. The test does apply. Therefore, the series must diverge as well. We have a theorem here, the so-called p-series theorem. And that is that the sum, n equals 1 to infinity of 1 over n to the p, is convergent if and only if p is bigger than 1. Note, p equals 1 is the harmonic series, right? That's just the sum 1 over n, 1 plus half plus a third, so on. We've already proven using kind of a more lengthy argument that that diverges, but we're going to see now that more directly that this will diverge. Okay, I kind of would really like to I would really like to just integrate 1 over x to the p and make that argument. But I have to be a little bit careful here. 1 over n to the p, I mean, p could be any real number. It could be a negative number. What's like 1 over n to the negative 2? That's like n squared. Is that decreasing? No, it's not. So, okay, let's look at f of x equals 1 over x to the p. On 1 to infinity, f is continuous. Sure. We're not starting at 0. We don't have that discontinuity at 0 to worry about. It is positive, but decreasing. That's very dependent on p. It's dependent on p, not dependent on n. It's not like for n equals 1 and 2, it's not decreasing, but from n equals 3 and further on out, it is. That was kind of the situation we had up here, where we could just throw off those first couple of terms and then we're fine. But here, that really depends on p. So let's take a couple of cases. The first is p less than 0. This essentially puts powers of n up top, and this is really the problem where we might not be decreasing. If p is less than 0, then 1 over n to the p is n to the minus p, or n to the something positive. And this is clearly not decreasing, this is increasing. Even if the positive number is like a half or something, still square root of n is increasing. But certainly n to the first or n to the second, those are increasing. So we can't apply the integral test here. Integral test does not apply. However, nicely enough, we have our divergence criterion or test for divergence. In this case, p less than 0, n to the positive does not go to 0, implies sum of 1 over n to the p diverges, and that's the end of the story there. So there is a bit of a nuance here, but nicely enough, this annoying special case can be handled pretty easily. For p is less than 0, where our 1 over n to the p is increasing rather than decreasing, we just apply test for divergence and these diverge. What about for p bigger than 0? P bigger than or equal to 0, let's say. Well, I guess p equals 0. Let's handle that separately. I guess p equals 0 is just like the sum of 1 a whole bunch of times. So this is just sum n equals 1 to infinity of 1. Clearly diverges. The sequence consisting of only ones does not go to 0. So by the same test for divergence, we get this. And then the interesting case, p strictly bigger than 0. This is the interesting case. So when p is strictly bigger than 0, f is always continuous and positive, but now it's also decreasing. Right, it's decreasing on 1 to infinity. So now we can apply the integral test. So in addition to the others that we already checked off, now f is decreasing when p is bigger than 0. We can apply the integral test. We can investigate the integral 1 to infinity, 1 over x to the p dx. And we had a theorem from our improper integral section at the end of chapter 7. We had a theorem that said that this improper integral converges if and only if, and if with two f's on it means if and only if, means the first thing is true if the second is true, and the first thing is true only if the second thing is true. So this converges if and only if p is strictly bigger than 1. But since the integral test applies here, and the integral converges if and only if p is bigger than 1, then the series sum n equals 1 to infinity, 1 over n to the p converges if and only if p is bigger than 1. When I write IFF for if and only if, I always underline it so that it doesn't just look like I, added on an extra letter by accident. But yeah, so we have our p series tests, that series that look like sum 1 over n to the p. They converge if and only if p is bigger than 1. And it's essentially riding the back of this improper integrals theorem, where this integral converges if and only if p is bigger than 1. But we did have this little, these little nuance cases that we had to deal with to make sure that we took care of the situations where the integral test does not apply. So even at first glance, it looks like, oh yeah, just replace this with an integral, and we know when the integral converges, it required a little bit more because, we couldn't apply the integral test to these first two cases. But we just handle those pretty easily with the criterion for divergence. And as an aside, this p-series statement, it kind of almost gives us another test, right? We can add this into our toolbox and say, if I have a series that looks like this, it converges if p is bigger than 1 and diverges if p is not bigger than 1, right? And p equals 1 means that p is not bigger than 1. The harmonic series diverges. So we can, if we needed to remind ourselves of the harmonic series convergence property in the future, if we remember p series, we can see right away that the harmonic series diverges, because p needs to be strictly bigger than 1 for convergence. In example 3, for what values of p is this series convergent? Sum n equals 2 to infinity of 1 over n times parentheses log n to the p. So here, clearly, we have the associated f of x is 1 over x times log x to the p like that. And I'm going to leave some details here to fill in. But the crux of this is we want to investigate integral 2 to infinity, 1 over x log x to the p dx. And here we can see by a substitution, if u is log x, du is 1 over x dx, well, this is going to give me what? It's just integral of 1 over u to the p du. When x is 2, u is log 2. And as x goes to infinity, log of something that goes to infinity also goes to infinity. And I know this converges if and only if p is strictly bigger than 1. So for what values of p is this thing convergent? P is strictly bigger than 1. There's one interesting thing I want to point out here is if we look at the p series test here, it might seem like this gives like a really clean dividing line between things that converge and things that don't. Things that converge, we might be tempted to say things that converge faster than harmonic series do converge. That's probably a funny way to say it. Think, series where the terms get small faster than harmonic series converge, and series where the terms get small slower than the harmonic series diverge. Period, end of story. That's like a stark dividing line between uh, any function that gives rise to the terms of a series. But actually, we see this thing down here. These terms are kind of, in a sense, closer to the harmonic series, uh, but they can still converge. So we can even look at something like 1 over n log log of n to the p, and that will have the same convergence properties. So the harmonic series isn't quite as stark of a dividing line as we might expect. We can kind of keep getting like closer and closer and finding series that converge or diverge, or however you want to look at it. So this gives a very clean line for the collection of functions that can be written as 1 over n to the p. But if we expand our view to kind of all functions that exist, it's more of a fuzzy line. Okay, let's jump down then to the next section, 11.4, the comparison tests. So we have two theorems here. We have two different comparison tests. And again, these are just like our other tools in our toolbox. Sometimes direct comparison test is a little more useful. Sometimes limit comparison test is a little more useful. When we can apply it, I think limit comparison test tends to be a little cleaner and a little less messy with the algebra and arithmetic. So if I could use either one and I was on an exam or something, I'd probably go with limit comparison test if it was available. But for our purposes, we'll kind of jump back and forth. And some of it, also some of these examples, they might be easier to show with maybe an integral test or something like that. So I'm not throwing any individual example out here and saying that the way that I choose to do it is the absolute best or most efficient way to do this to prove the convergence property of a given series. These are more illustrative. Okay, so what are our theorems? In both cases, our assumption is that we're dealing with positive series. As we're making comparison here, we have two series that we're comparing, some AN and some BN, and in both cases, we're assuming they're both positive. It's really enough for them both, or for each of them individually to have the same sign far enough out in the tail. So if I can say, okay, AN, after n equals 100 is always negative, I think it's pretty clear that I could, argue that that's effectively the same as AN being positive for the whole series. The same convergence property is going to apply because I just chop off the first 100 terms. That's just a finite number. And then I have what's left of the series. That's my remaining series. And if things are negative, well, if I'm thinking in terms of my partial sums, if all of the terms are negative, I just factor out a -1 and now all the terms are positive. So, when we say these are positive series, there's a bit of a fudge factor there that we can work with. What does the direct comparison test say about comparing two positive series? Keep in mind these are positive numbers, and if also AN less than or equal to BN, and if some BN converges, then some AN converges. In other words, what we're saying is that if the terms of the A sum are kind of squeezed in a sense between 0 and the terms of the B sum, if the B sum converges, then B's terms get small enough, fast enough to converge. It's really squeezing A closer into 0, so A must also get small enough, fast enough to converge. It feels like a squeeze theorem argument, right? A is stuck between 0 and B. B is getting small very fast. A has to get small very fast as well. No other choice. On the other hand, if AN is bigger than or equal to BN and some BN diverges, then some AN diverges. Kind of this direction is a little more nuanced, but maybe the kind of gut feeling is that if AN is above BN and BN is not getting small fast, then AN can't be getting small fast, or it would have to go below BN at some point. So BN's divergence implies AN's divergence in this case when AN is bigger than or equal to BN. Our limit comparison test is kind of nice because these inequalities are often messy to show. In my limit comparison test, if I have two series, some AN and BN that are positive series again, and if the limit of their ratio, limit that goes to infinity of AN over BN, equals L a positive real number, what does that kind of mean? That kind of means that out in the tail, if limit AN over BN equals 3, that means just kind of like AN looks like 3 times BN, but just like a constant multiple. If BN's getting really small really fast, 3 times something getting really small really fast also gets really small really fast. So note that if this limit exists and is a strictly positive real number, so this means open 0 to infinity with this open, we'll put a triple exclamation point on there. I mean, if this is 0, well, that just means that A might get really small really fast and B might, not get very small very fast. And well, so if this is 0, it doesn't tell you much. Also, if it's infinity, it doesn't tell you much. Basically, what we're saying is if AN and BN go to 0 kind of at the same level of fastness, the limit of their ratio is just going to be some positive real number, and the series will behave similarly in terms of convergence or divergence. Okay, let's take a look at an example here. So these are nice theorems, but we don't get something that's as clean or as clear cut, let's say, as say the integral test. The integral test tells me directly how to evaluate if a series is convergent. How do I use these properties of comparisons to help me actually answer a question? Well, I have a series given to me. This might be like some AN. Let's say 10, not a funny little thing next to the plus. I have a series, some an. My job is to come up with a bn that kind of feels like the an series to me, and that I can more easily tell the convergence of. So bn, speaking very roughly here, of course, feels like an, and I know convergence of bn. I know the convergence properties of bn. Maybe I know the bn diverges, or maybe I know the bn converges. I look at an and I say, well, if I put in a really big n cubed is really, really big. Is the plus 10 really consequential? Not really. So I might think that perhaps bn equals 1 over n cubed might be a good series to compare with. Let me write that a little neater. Now I might come up with a bn and try to do a comparison, and it just doesn't work, and I have to try again. That's a possibility, but this feels like the right one to use here, maybe. So bn 1 over n cubed kind of feels like it should be acting pretty similar to an way out in the tail, which is where we care about convergence. For large n's, 1 over n cubed plus 10 is basically 1 over n cubed. And I know, importantly, sum n equals 1 to infinity of bn. This is just a p series with p bigger than 1 converges. If I found a bn that looked like an, like 1 over n cubed plus 11 or something, but I don't know the convergence properties of bn specifically, that doesn't really help me much. Okay, but this bn, I know its convergence property, and I think it feels like an. I notice that an is less than bn, or particularly less than or equal to bn, right? And I also know that an and bn are positive numbers for n bigger than or equal to 1. So I have positive series where an less than or equal to bn, and some bn converges. Positive series, an less than or equal to bn, some bn converges. Well, hey, by the direct comparison test, basically part A, some an converges. Okay. What about this one? Some n equals 1 to infinity of 1 over n cubed minus 10, not plus 10. Basically the same series, but this is kind of why direct comparison tests can be annoying. I really want to use bn equals 1 over n cubed. That feels like the right one to use for the same reason that I argued it felt like the right one to use before. But now, well, the denominator in an, these are my ans, is just a tad smaller than that in bn, making an a bit larger than bn, and bn, some bn converges. But when an is bigger than bn converging doesn't tell me anything. It's only when an is smaller than bn that bn converging helps, right? So like direct comparison tests, we'll put like a frowny face on there. Could I force the issue and, I don't know, make like a bn like 1 over n squared or something, maybe? But the nice thing is that I have another direction I can go. I can use a limit comparison test. I think that the limit of these will work just fine, right? I don't have to worry about these pesky, like, oh, this is plus 10 versus minus 10, and that throws off the inequality. I mean, 1 over n cubed and 1 over n cubed minus 10, or 1 over n cubed plus 10, for a big N, they're all basically the same. I can apply this heuristic method of thought much more easily if I look at my limit comparison tests. Now, importantly, I do know that an and bn are positive, or positive. So I do have my one assumption satisfied. I need to look at the limit of their quotient. An over bn. Well, that's 1 over n cubed minus 10. And then bn on the bottom is 1 over n cubed. So that's an n cubed up top. This limit is clearly 1. Right? Can divide the top and bottom by n cubed. 1 over 1 minus 10 over n cubed. And then 10 over n cubed goes to 0. 1 is certainly a number that is in the positive reals. It is certainly in open 0 to infinity. We have two positive series, the limit of whose quotient of their terms is a positive real number. Their convergence properties will be the same. I know sum n equals 1 to infinity of bn converges. This implies by the limit comparison test that sum an converges as well. So the limit comparison test, because we're operating underneath the limit and kind of in a manner of speaking, our lower order terms just kind of go away under a limit, very loosely speaking there. We don't really care about the details of whether this is a plus 10 or a minus 10, or even if I had an, n cubed plus n or an n cubed minus n, or it doesn't really matter. The limit comparison test lets me kind of brush all of those lower order terms under the rug. Where the direct comparison test, I do have to deal with those. But that's not to say that the limit comparison test is best in every single case. So let's evaluate the convergence of this series, sum n equals 1 to infinity of log of n over root n. Note that log of 1 is 0. Our first term here is 0, but it's not like we're dividing by 0 or something. The 0 is in the numerator, so we could start this at n equals 2 and have exactly the same the same partial sums, or we could start it at 1. This one up here, with the integral test, like this one had to start at 2 because the log n was in the bottom, or like this one up here, right? If one of our terms is something divided by 0, then all the partial sums don't even make sense. But for this one, having one of our partial sums or one of our terms be 0, no big deal. Okay, so if I look at this, one thing that I kind of know from Calc 1 and our discussion of limits and L'Hopital's rule and things like that is that n to a power grows faster than log n, like basically in all circumstances, right? N to a positive power. So I think the root n is going to completely dominate the log n here. This isn't like n squared over root n or something like that, where I have two powers battling it out. I have a log against the power, and the log is like always smaller than the power for large inputs. I think this is going to look kind of like 1 over root n. But log n over root n goes to 0. So log n over root n goes to 0. If I have log n over root n over 1 over root n, this goes to infinity. So if I'm trying to use some kind of limit comparison test, well, number one, I guess my test for divergence, maybe I shouldn't put a check there. I should put a question mark there. My test for divergence doesn't really give me anything fruitful. This might converge, it might not converge. If I was looking to use a limit comparison with a series sum bn, where bn is 1 over root n, I don't get a convergent limit. I don't get something that converges to a positive real number. It goes to infinity. But I still think this is the right thing to do. So let me consider some Bn, where Bn is 1 over root n. Limit comparison test isn't going to work. But I do actually notice that these are both positive series. Well, they're both positive series. I mean, Bn is always positive. An, this one up here, this is An. And it's negative for the first, or for one of the terms, for the n equals 2 term, but for n bigger than or equal to 3, they're both positive series. And An is bigger than or equal to Bn because, again, for n bigger than or equal to 3, because log of e is 1 and log is increasing, e is about 2.7. So log of 3 is bigger than 1. If I multiply 1 over root n by a number bigger than 1, positive number times a number bigger than 1 gets bigger. So they're both positive series, and An is bigger than or equal to Bn, but I know some Bn, well, this is a p series with p equals 1/2, which is less than or equal to 1. I know some Bn diverges. So I have positive series, two positive series, where An, the series of interest, is bigger than or equal to Bn, the terms of the series that I'm comparing to, both positive series. An is bigger than or equal to Bn, and I know that some Bn diverges. The direct comparison test tells me that some An diverges. Direct comparison test like part B says that some An diverges. I think that's the messiest way that I've ever written diverges. Diverges. So by the direct comparison test, that was just the right one to use in this case, right? If I tried to use limit comparison test, taking the ratio of log n over root n to 1 over root n, the root n's cancel and I just get log n, which goes to infinity. That's not helpful for my limit comparison. But a direct comparison works just fine here. Okay, let's look at example 4 here. We have a claim. The claim is that if sum n equals 1 to infinity an converges, and there exists a number capital N such that a sub n is in open 0 to 1 for all n bigger than or equal to capital N. So if I go far enough in the tail, the terms of my series are in open 0 to 1, then the claim is that the sum of an squared also converges. So what are we doing? We know something about some an, and we have this other series, Bn equals an squared. But an squared is less than an, right? Because if I take a number strictly between 0 and 1, and I square it, I multiply it by itself. I'm multiplying a positive number by a number less than 1 in magnitude, then that gets smaller. I also know that an and an squared are in open 0 to 1. So specifically, they are bigger than 0. So I have positive series. I have Bn less than or equal to an, and I know by assumption of the statement, some an converges. I have positive series. I know was I think I got my A's and B's backwards here. Yeah, I know that my A's and B's are just backwards, the way that I wrote them down here. Um, but I know that the larger one converges. I got my A's and B's backwards of the way I have them written in the theorem. So swap all of the A's for B's and the B's for A's. Um, but the larger one, its associated series converges. Both are positive series. This implies by direct comparison test, since the larger one converges, the smaller one must as well. Some Bn converges. Yeah, it's really this one that I'm asking about. That's what I should have called Bn, or yeah, the one that I'm asking about is what I should have called An, but I already used An, so I should have called it like some Cn or something like that, so that I wouldn't have got them backwards. But there we go. So An is bigger than or equal to Bn. In this case, Bn is the smaller one. We know that the bigger one converges, therefore the smaller one must also converge. Okay. Um, I think we can get through this one in a couple minutes. So if I look at this series, sum n equals 1 to infinity of n over n squared plus 1. If I think of large n's, the plus 1 on the bottom is pretty immaterial, right? If I have n is 100, I have like 100 over 10,000 plus 1. That's basically just 100 over 10,000. Or n over n squared feels like 1 over n. So if I call this an, I'm going to consider bn equals 1 over n. It feels like n over n squared plus 1 and 1 over n should behave pretty similarly for large n's. These are both positive series, and if I take their ratio, I have n over n squared plus 1 divided by 1 over n, or that's times n. That's n squared over n squared plus 1. Or I could write that as 1 over 1 plus 1 over n squared. And this clearly goes to 1 as n goes to infinity, which is a strictly positive real number. So the limit of the ratio does exist. It's 1. It's a strictly positive real number. And these are both positive series. My limit comparison test says that they both have the same convergence properties, but I also know the sum of Bn diverges. It's the harmonic series, or it's a p-series that diverges. So this implies by my limit comparison test that some An diverges as well. And maybe I'll leave this one as an exercise. And as a hint, use a limit comparison test. And use a limit comparison test with a function that we've already seen in one of the previous problems, a limit comparison test used with. So look at sum n equals 1 to infinity of 1 over log of n plus n. Think of which one of those terms is going to dominate the other for large n, and think about what function you might compare to, use a limit comparison test, and then make the argument of whether this converges or diverges. So we'll leave that as an exercise. Okay, let me stop the recording here.